Okay, so we have a real analysis practice final exam. Let's start with number 1 here. So we have let A equals this 2n plus 1 over n plus 2, these conditions for n and n, and for n rather. And for part A, show that A is bounded above and below. Okay, so think in terms of this is going to be a supremum and infimum problem. So what we do here, we let A equal what it's given. So we're first going to simplify that 2n plus 1 over n plus 2. That's going to be 2 minus 3 over n plus 2. By the way, I'm going to go through this rather quickly, just so you have a reference, and then you could try it yourself. This way you could check the answers or whatnot, but we'll go quickly. This form makes the behavior much cleaner if you break this up. And since n is greater than or equal to 1, 3 over n plus 2 is greater than 0. Therefore, 2 minus 3 over n plus 2 is less than 2. So 2 is an upper bound. Also, right here, 3 over n plus 2 is less than or equal to 1. For n is greater than or equal to 1, we have hence here 2 minus 3 over n plus 2 is greater than or equal to 1. So 1 is a lower bound. So thus A is bounded above and below. So that takes care of part A. There's the work. For part B, find the supremum A and infimum A. So this for part B. Let's see what we can do. As n approaches infinity for that 3 over n plus 2, okay, we get that approaching 0. So 2 minus 3 over n plus 2, that's approaching 2. So here, thus, for this situation, the values of the sequence approach 2 from below. Hence, the supremum of A is 2. Now we check the smallest term. Since 2 minus 3 over n plus 2 increases as n increases, the smallest value occurs at n equals 1. Substitute that in. 2 times 1 plus 1 over 1 plus 2, you get 3 over 3 is 1. Therefore, the INF A is 1. So, for part C, determine whether supremum or infimum belongs to A. Well, we have that 1 in A obtained when n equals 1, 2 not in A, because 2 minus 3 over n plus 2 is less than 2 for every finite n. So, INF A, 1 in A, sub A, 2 not. Okay, so that takes care of number 1. Again, I'm going to go through this fast. Okay, number 2. Define the sequence recursively by x sub 1 equals 2, x sub n plus 1 equals 1 half times the quantity x sub n plus 5 over x sub n. So, part A, show that x sub n is greater than 0 for all n. So here's what we could do here for part A. We have all this information, write it, and then we have this is Newton. This is going to wind up being Newton's method when you identify that pattern for square root of 5. So we're going to show that x sub n is greater than 0 for all n. Since x sub 1 equals 2, that's greater than 0. And if x sub n is greater than 0, then x sub n plus 1 equals 1 half times the quantity x sub n plus 5 over x sub n. That has to be greater than 0. So just using mathematical inductions, by induction, x sub n has to be greater than 0. Part B, show that x sub n is decreasing and bounded below. So for part B, compute x sub n plus 1 minus x sub n, that equals 1 half times quantity x sub n plus 5 over x sub n minus x sub n. Okay, that's going to be 5 minus x sub n squared over 2x sub n. X sub 1 equals 2, which is less than root square root of 5. So this recurrence does not decrease. In fact, it decreases here. And if we check, does not decrease, it increases. It increases. So check. X sub 2 equals 1 half times the quantity 2 plus 5 over 2. That's 9/4. That's 2.25, and we're good to go. That's greater than 2. So that helps validate with checking. Part C, determine the limit as n approaches infinity for that x sub n. Okay, here's what we do. We let limit of x sub n equal L. L is 1/2 times the quantity L plus 5 over L when we substitute. Think about over here, substitute. And now we just solve for L. When we solve for L, we're going to take the positive value of it. Since L is greater than 0, take L as square root of 5. Okay, so that takes care of that. Number 2 is good. We're ready for number 3. Again, I'm going to go through these quickly since you have pretty much most of the setups and the answers there. So 3. Suppose A sub n is a bounded sequence of real numbers. Part A, state the Bolzano-Weierstrass theorem. So the Bolzano-Weierstrass theorem, every bounded sequence of real numbers has a convergent subsequence. Okay, for part B, prove that the sequence B sub n equals negative 1 to the n times n over n plus 1 has at least 2 distinct subsequential limits. So for part B, here's what we do. Separate the even and the odd terms. If n equals 2k, let b sub 2k equal 2k over 2k plus 1. That's going to go to 1. If n equals 2k plus 1, b sub 2k plus 1, that's negative 2k plus 1 over 2k plus 2. That's going to go to negative 1. Okay? You have alternating signs. So what we could say, the sequence has at least 2 distinct subsequential limits. Okay. And for part C, find all subsequential limits of B sub n. So for part C here, the only possible subsequential limits are what was found in part B are from the even or odd subsequences, negative 1 and 1. Okay, so that takes care of that one. That is number 3, yes? Okay, sorry. Is that all? Yep, that's number 3, A, B, and C. Okay, number 4. Sorry about that. Okay, number 4, we have this piecewise function. F of x equals x squared sine 1 over x, where x cannot equal 0 for the domain, and the rest would be 0, where x equals 0. Okay, so part A, prove that f is continuous at 0. So for part A, continuity at 0. We're going to use the squeeze theorem for this. Find that limit as x approaches 0, x squared sine of 1 over x. Set it equal to 0. Since now squeeze theorem, think about that. Negative 1 less than or equal to sine of 1 over s is 1 over x is less than or equal to 1. So then we have these multiply that x squared, negative x squared less than or equal to sine of 1 over x less than or equal to x squared. Okay. So we do the now moving forward, take care of these the x squareds. Okay. As x approaches 0, negative x squared goes to 0, positive x squared goes to 0. So by squeeze theorem, the limit as x goes to 0, f of x equals 0 equals f of 0. So f is continuous at 0. Pardon me if I misspeak, if I go too fast. Okay. With these two parts, assuming from the squeeze theorem, the math works out there. Part B, determine whether f is differentiable at 0. Okay, so differentiability, we're going to use the limit definition of the derivative. You know what that is. And then just substituting, and we wind up with the limit being 0. And that leads right into part C. If differentiable, compute f prime of 0. Well, it's 0. Comes out to 0 for part C. Okay, so 4. That was number 4. Good to go with that. Now we can move along to number 5. Okay, for 5, let E equal this. Part A. Okay. Determine whether E is open. Okay, for part A, is E open? So the answer to this would be no. For example, we have this. Any interval around 1 contains numbers not of the form 1 over n. So E is not open. Part B, determine whether E is closed. Well, is it closed? Actually, it's not closed. The sequence 1 over n is going to 0. However, this 0 doesn't belong to E, so E does not contain all its limit points. So E is not closed. Part C, find the set of accumulation points of V. That would only be 0. Okay. Moving quickly. Number 6. Okay, let F be 0 to infinity, map to R, be defined by f of x equals square root of x. Part A, prove directly from the definition that f is uniformly continuous on 0 to infinity. Let's see. So here, write out what we have, and here's what we could do. To prove uniformly continuous for this, for x, y, we have to be greater than 0 here. We're going to take the absolute value of square root of x minus square root of y, and that's to be set equal to the absolute value of x minus y over the square root of x plus the square root of y. And this is a helpful inequality we're going to use here. For this, take the absolute value of square root of x minus square root of y. That's less than or equal to the square root of absolute value of the difference between x and y. Okay, so here, given epsilon less than 0, we're going to choose a delta. Apologize for my very poorly drawn deltas. Delta equals epsilon squared. So here, if the absolute value of the difference between x and y is less than delta, then the absolute value of the difference between the square root of x and the square root of y, that's less than or equal to the square root of the absolute value of x minus y, is less than the square root of delta, equals that epsilon. So therefore, square root of x is uniformly continuous on the interval 0 to infinity. Okay, and think about what that would look like if you were to graph it. Okay, so for part B, determine whether the g of x equals x squared is uniformly continuous on the interval 0 to infinity. Justify your answer. So for part B here, this is what we do. If x sub n equals n, y sub n equals n plus 1 over n, okay, then we take the absolute value of that x sub n minus y sub n. That equals 1 over n. That's going to 0. However, the absolute value of x sub n squared minus y sub n squared, that equals this. N squared minus the quantity n plus 1/2 squared. Take the absolute value of that. We expand these terms, compute, and we're going to get, after taking the absolute value, 2 plus 1 over n squared. That's going to 2. So that 2 plus 1 over n squared going to 2. We could conclude, so small changes in input do not force small changes in output. So we could say x squared is not uniformly continuous on the interval 0 to infinity. So that takes care of number 6. Moving to number 7. And moving to number 7 here. For each series below, determine whether it converges absolutely, converges conditionally, or diverges. Justify each conclusion using an appropriate test. So for letter A, we have this, n equals 1 to infinity, and for this is negative 1 to the n over square root of n. So what we do here, think about what this would be an alternating series. This converges by the alternating series test because 1 over square root of n goes to 0, and 1 over square root of n is a decreasing So, however, it does not converge absolutely, and here's why. Think of P series. This would be 1 over n to the 1/2. So it's a P series with P equals 1/2. That's less than 1, so that would diverge for the P series. So this is conditionally convergent. Okay, for part B, here we have n equals 2 to infinity, and then we're having 1 over n times the natural log. My apologies, that's natural log of n. So for here, Use the integral test for this one. This diverges by the integral test. You could do the calculus here. When you integrate this, natural log of the natural log of x from 2 to infinity, after performing the computation, that comes out to infinity, so that diverges, it's divergent. Okay, and this last one here for number 7 for C, n equals 1 to infinity, and then you have n squared plus 1 over n cubed plus 4. So for a large n, if we reduce this, this is compared to 1 over n, using the limit comparison with this summation of 1 over n. Okay, this is going to be limit as n approaches infinity, n squared plus 1 over n cubed plus 4 divided by 1 over n. We just perform, do the computation, and as the limit as n approaches infinity, that's going to go to 1 because it's going to be same degree, take the ratio of the coefficients, and since 1 over n diverges, this diverges. Okay, so letter C diverges, that's number 7. Okay, moving along to number 8. So for number 8, okay, we have f 0 to 2, real numbers, is continuous on 0 to 2 and differentiable 0, 2 here. F of 0 equals 1, f of 2 equals 5. You've probably seen a ton of problems like this. This is actually an extension from Calculus 1. A lot of courses cover mean value theorem in Calc 1. So for part A, state the mean value theorem. You've probably seen it so many times. Here it is. Here's the mean value theorem, MVT. Part B, prove that there exists this such. This is just an extension of the mean value theorem. That's Calc 1. So do f prime of c, that equals just f of 2 minus f of 0 over 2 minus 0. You get 2. Okay? And that's it. That's in 0, 2, such that f prime of c equals 2. Done. That's part B. Okay. Part C is more of the real analysis stuff as far as, well, everything is, this is real analysis, but this would be probably one of the newer things, the new things that you would learn in a real analysis course, how to do part C. Suppose, additionally, that f prime of x is less than or equal to 3 for all x in 0, 2. Show that f of x is less than or equal to 1 plus 3x for every x in that 0, 2. So apply the mean value theorem to the interval 0x. We're going to get f of x minus f of 0. That's going to equal f prime of c times the quantity x minus 0. And for some c in that 0x interval, since f prime of c is less than or equal to 3, right, from what we're given, f of x minus 1 is less than or equal to 3x. Okay, if we get that by itself, that 3x. Therefore, f of x is less than or equal to 1 plus 3x. Okay, so that takes care of number 8. Number 9. Okay, that I sub n. I sub n equals that bracket a sub n, b sub n bracket b square. Be a sequence of closed intervals such that I sub n1. Okay, let's go into I sub n for every n, and n approaches infinity for the difference between b sub n minus b sub n and a sub n equals 0. Okay? Prove that there exists exactly one real number contained in every interval I sub n. Okay, so interesting one. So the nested intervals here, so we're going to let I sub n equal this. And then I sub n plus 1, I sub n. And we're given these are the 3 things we're given, right, from here. So here's what we'll do. We'll prove exactly one real number lies in every interval. Okay? Due to the intervals being nested, the left endpoints increase and the right endpoints decrease. So we say a sub 1 is less than or equal to a sub 2 is less than or equal to a sub 3 is less than or equal to a sub 4, and going on and on. And then for b sub 1, okay, that's greater than or equal to b sub 2. B sub 2 is greater than or equal to b sub 3. B sub 3 is greater than or equal to b sub 4, and on and on and on. So a sub n is going to be less than or equal to b sub n. That's also. And since a sub n is increasing and bounded above, that's going to converge. So let a sub n go to L. Since 0 is less than or equal to b sub n minus a sub n, that goes to 0. We also get b sub n approaching L. So for every n, a sub n less than or equal to L, less than or equal to b sub n. Let that L, right, be an I sub n for all n. Now suppose the two numbers L and M are both in every interval, okay? Then the absolute value of the difference between L and M, that's less than or equal to b sub n minus a sub n for every n. And since b sub n minus a sub n goes to 0, okay, what we could do is let, in this situation, we could let that L, the difference here, L minus M, absolute value equals 0. So that L equals M. So, as a result, therefore, exactly one real number lies in every I sub n. So that's going to equal n. Okay, so that takes care of number 9. Number 10. Okay. All right, we have this set of E. It's called connected if whenever that E, right there, is in that union of U and V, okay? Where U and V, okay, U and V here are disjoint, non-empty sets, then either that E in U or E in V. Okay, so let's see. F in this interval, 0 to 1, R is continuous. Prove that F here, right? Think of image set here, or in other terms, so F of that interval 0 to 1 is an interval. Use the intermediate value theorem. So we'll let A be epsilon F of interval 0 to 1 with A is less than B. Okay, then there exists x sub 1, x sub 2, epsilon of the interval 0, 1, such that F of x sub 1 equals A, F of x sub 2 equals B. Take any number y on this interval. A is less than y is less than B. Okay, assume x sub 1 is less than x sub 2, and since F is continuous on x sub 1, x sub 2, by the intermediate value theorem, IVT, there exists this C epsilon in the interval x sub 1, x sub 2, such that F of C equals y. So, what we could say here, thus, every value between A and B is also in F of interval 0 to 1. Therefore, F of that interval, brackets 0 to 1, that's an interval. This proves the continuous image of a connected interval is connected. Okay, so pardon me if I just used symbolic language for that, for each piece. But that's number 10. That's how you could do number 10. Okay, so, and this is the last one, number 11. Okay, so number 11 here, let's see. Let f of n be a sequence of functions on 0 to 1 defined by f sub n of x equals x to the n. Part A, determine the pointwise limit of f of sub n. So the pointwise limit for 0 is less than or equal to x is less than 1. X sub n goes to 0. For x equals 1, 1 to the n equals 1. So the pointwise limit is f of x equals, for 0, interval 0 is less than or equal to x is less than 1. For 1, just define it x equals 1. For part B, determine whether the convergence is uniform on the interval 0 to 1. Part B would be no. f sub n of x equals x to the n is continuous on 0, 1, but the pointwise limit is discontinuous at x equals 1, right? From what was in part A. So a uniform limit of continuous functions must be continuous. Therefore, it's a no. And part C, determine whether the convergence is uniform on 0 to a for every a less than, this is just supposed to be a less than, my apologies, for every a less than 1. The answer to C would be yes. Okay, that x in that interval 0 to a. 0 is less than or equal to x to the n is less than or equal to a to the n. And since we have here 0 is less than a is less than 1, a to the n goes to 0. And this here, we have our SUP, absolute value of x to the n minus 0. That equals a to the n. That approaches 0, x in 0a. Therefore, f sub n goes to 0 uniformly on that interval 0 to a for every a is less than 1. Okay, so I went through this very rapidly, but you have the answers in a lot of the setups. Hopefully this could assist you as a review for your exam, or just a refresher, or just some fun to do some problems. Okay, thank you very much and have a great day.